Okay, so today we're talking about limits. What is a limit in math, calculus? Okay, you don't have to write this first sentence down. Actually, you don't need to write any of this down yet. So I put into my calculator some function, and you don't know what it is. Secret. I put it into y1. And here's what I want to know. I want to know what is our function approaching as x approaches the number 2. Okay. I don't know what it looks like. But as we plug in values closer and closer to x, what are these values getting close to? What is this number? Okay. And as we approach from the other side, what is this approaching? Okay. So this is the whole idea of a limit, is as x gets closer to some number, what is our function value getting closer to? Okay. And this is the notation we use. LIM stands for limit. And this is x. We have a little arrow always approaches some number. We put a number here. And sometimes you'll see a positive or a negative sign. We'll say what that means. And of this function. So we want to know what x approaches to as x approaches 2. So what number should I plug into my calculator? Kind of like we did on the quiz. We kept plugging in numbers closer and closer to 4. So let's try like 1.9. 1.99. 0.999. Oops. Okay. So I'm plugging in closer, x values closer and closer to 2, right? And what does it look like after x is getting closer and closer and closer to? 7. Okay, so oops. So whatever this function is, we think this is getting closer and closer to 7, even though we have no idea what happens at 7. And we don't care what happens at 7. All we care is what's happening as we get closer to it. We actually only approached it from the left side, numbers less than 2. Okay. We also need to approach it from the right side, numbers greater than 2. So, okay. So as we plug in numbers from the right, the numbers are slightly greater than 2. And the closer we got to 2, what is our function getting closer and closer to? 7 as well. Okay. Limits, we don't care what happens at this number, 2. We only care what's happening from the left and from the right. Okay. So, so whatever this function is, and so we use certain notation. If we approach from the left, we put a little, looks like to the power of a negative sign. Okay, this is mean we're approaching, x is approaching 2, but numbers less than 2 of this function. Okay, and the answer was 7. If we approach from the right side, it's called the right-hand limit. This was also 7. Okay, so limits, all we care about is what's happening as x gets closer to some number, both from the right and from the left. If these both are the same number, this limit, which is just approaching 2, not from the left, not from the right, but both sides, is equal to 7 as well. So this is called a left-hand limit. It's called the right-hand limit. Okay. And if the limit as x approaches whatever number this is from the left equals the limit as x approaches a from the right, then the limit as x approaches a, which is from both the left and the right. Okay. And we don't care about what f of 2 actually is. Okay, when we find limits, we don't care what f of this value is. All we care about is what's happening from the left and from the right. In fact, what is f of 2 here? Doesn't even exist. Okay, so whatever the function is, it doesn't exist there. And that's okay. We don't care. We will care later, actually. It'll tell us whether the function's continuous or not. But so when we're finding limits, one way is this way. If you're given the equation, just to the left of it, just to the right of it, and if they keep getting closer to some number, that is the limit. What was this secret function? Anybody know? No idea. Let's see what it is. Well, what kind of function was this? What do we call this step function? Rational, thank you. What is a rational function? What's the root word of rational? Ratio. Any function that could be written as the ratio of two. Uh-oh. Okay, like x squared over e to the x is not a rational function. It's not just a ratio of functions. Not just expressions. This is an expression. Ratio of two polynomials. Thank you. Okay, as long as these are both polynomials, it's called a rational function. In rational functions, just as a review, they have one of two things. They either have vertical asymptotes, or what's the other option? Uh-oh. What help me? Well, where is this? Okay, so when values that make the denominator 0 will either be a vertical asymptote or a hole in the graph. Thank you. Okay. Does this function have a hole in the graph or a vertical asymptote? A hole. Okay, at 2. It doesn't look like this. It looks like a hole in the graph. How can we tell from here that it has a hole? That's a hole in the graph. If this wasn't here, it would be a vertical asymptote. What would happen? In fact, let me put that in the calculator. There it is. Delete. Okay, so now it no longer has a hole. There's going to be a vertical asymptote at x equals 2. What's going to happen when I plug in numbers close to 2 now? Any guesses? Okay. What's happening with the y value? Just keeps getting larger, except it's negative, so it's really getting smaller and smaller and smaller and smaller. Okay, in fact, and then what's if I plug in numbers greater than 2? Like 2.01, 2.001, 2.001. It just keeps getting larger and larger and larger. Okay, so if this happens on the calculator, if you're given a secret function, you're plugging in value, or you could plug in the number, it doesn't matter. Let's talk about that limit actually. So if this is my function, what was it, x squared plus 3? Minus 3. Okay, and I can either write f of x here, or I could write in the whole thing. Okay, so we plugged in values, they kept going smaller and smaller. So we say the limit is actually equal to, some people say that if you get this, some people say the limit does not exist. Okay, but we always just write negative infinity. Don't worry about that. Okay, and so what is the limit as x approaches 2 of this function? If this does not equal this, it does not exist. Okay, so today we're only talking about limits based on graphs of the function or based on tables of values. The last example is tables of values. You get plugging in numbers, or you're given the tables of the x and the y values. Friday we'll start learning based on equations, or function equations. All right, first question. What is the limit, or let me write down here. The limit as x approaches 2 from the left of g of x. So as x gets closer and closer to 2 from the left, what is this getting closer and closer and closer to? 3. So this limit equals 3. The limit as x approaches 2 from the right, as x gets closer and closer to, f of x gets closer and closer to 1. And what is the limit as x approaches 2? Does not exist. We don't have to look at anything except this number does not equal this number. The left-hand limit does not equal the right-hand limit. The limit as x approaches 2 does not exist. Okay. And what is g of 2? Where's the red dot at 2? There is none. So this does not exist as well. So at every x value, we always have a left-hand limit, a right-hand limit, the limit, and the actual function value. And they all might be a number, they all might not exist, and so on. Let's look at 5 here. The limit as x approaches 5 from the left. As x approaches 5 from the left, these values get closer and closer to 2. What is the limit as x approaches 5 from the right? As x approaches 5 from the right, or f of x or g of x approaches 2. So what is the limit as x approaches 2?
1.
This, sorry, 2. My bad. 5. My bad. Since the left-hand limit equals the right-hand limit, the limit is exactly equal to 2. Okay. And what is g of 5? 1. Okay. Is our function discontinuous at 5?
Yeah.
Definitely. Okay. And how can we tell? Well, obviously we look at it. But if all I gave you was this information, the way we tell if it's continuous is, does this equal the limit? Okay. If the function value equals the limit, it is continuous. If the function value does not equal the limit, it is discontinuous. Okay. And then our previous example, right? Our function value doesn't exist, definitely discontinuous. But this doesn't equal, well, this doesn't exist either. So, but in fact, that's going to be the definition of whether or when a function is continuous is if the if the limit equals the function value. We'll define that later. Okay, let's do another one. What is the limit as x approaches 0 from the left? Okay. So as x approaches 0, f of x gets closer and closer to? Let's call it 2.5. The limit as x approaches 0 from the right. As x approaches 0 from the right, f of x gets closer and closer to 2.5. And what is the limit as x approaches 0?
2.5.
2.5. And what is g of 0?
2.5.
2.5. Is it continuous at 0? Definitely. Okay. And in fact, if we know the function is continuous, let's say at 2 and 5 are its only discontinuities. Okay. Or let me ask you this: the limit as x approaches 0 of x to the 5th minus 7x plus 4. Is this a continuous function? What do we call this type of function? a polynomial, okay, all polynomials are continuous over all real numbers, okay. Since we know it's continuous at over all real numbers, we know this limit exactly equals whatever f of 0 is. Let's call this f. And what is f of 0? It'll be 4. Okay. So if we know a function is continuous at any value or over all values, the limit as x approaches that number will always equal the function value. And the limit, yeah. Okay. So like at 4 here, it's definitely continuous there. So the limit as x approaches 4 from the left is going to equal the limit as x approaches 4 from the right. It's going to equal the limit as x approaches 4. It's going to equal g of 4, whatever that number is. Let's call it 1.8. I'm just making up a number. Okay. So if we know it's continuous, the limit from the left equals the limit from the right equals the limit equals the function value. So every other number here besides 2 and 5, the limit from the left will equal the limit from the right, will equal the limit, will equal the function value. Make sense so far? Okay. If you're given a graph, okay. In fact, actually, let's do this example. What is the limit as x approaches? Oh, let's go to 2. Oh, no, let's go 1. The limit as x approaches 1 from the left is 1. 1. It keeps getting closer and closer to 1. As x approaches 1 from the right, 1. What is the limit as x approaches 1? 1. What is f of 1? 1. No. Okay. We have a hole in the graph right here. You can never tell on Desmos or the graphing calculator there's a hole. So be real careful. Okay, because it's so small, no matter how far I zoom in here, where is it? You will never see the hole. Okay, so be real careful on graphing calculators and Desmos. You will never see holes in the graph. Okay, so that's why when we draw them, like here, we make the hole giant, so you know it's a hole. Does that make sense? Okay. Where am I? You don't have to draw this. We'll just do it real quick. What is the limit as, this is 0, 0, right? As x approaches 0 from the left, let's call this f. As x approaches 0 from the left, f of x approaches -1. What is the limit as x approaches 0 from the right? As x approaches 0, this approaches -2. So both of these limits exist. Anytime you get a number, it exists. Okay. And what is the limit as x approaches 0? Does not exist. Okay, why? Because the left-hand limit does not equal the right-hand limit. Okay. And what is f of 0? -1. Okay. Is it discontinuous at x equals 0? Definitely. That's some sort of jump discontinuity, we call it. We'll talk later. We actually say it's continuous from the left because the limit from the left equals the function value. It's discontinuous from the right because the limit from the right does not equal the function value. But overall, it's definitely discontinuous. What is the limit as x approaches 2 from the left? 2. The limit as x approaches 2 from the right? 0, and the limit as x approaches 2 does not exist. Why does it not exist? The left-hand limit does not equal the right-hand limit. Okay, and what is f of 2? 1. It's definitely discontinuous at 2. Is it continuous from the left? No, because the left-hand limit does not equal the function value. Is it continuous from the right? No, because the right-hand limit, 0, does not equal to the function value. Okay. Unlike at 0, it is continuous from the left. What is the limit as x approaches 4 from the left? This gets closer to 3. Limit as x approaches 4 from the right? 3. What is the limit as x approaches 4? 3. And what is f of 4? 3. Okay. Is the function continuous at 4?
Yes.
Yes. If we weren't given a graph, if this limit equals the function value, it's continuous. Okay. And we're going to define later. So that means it's continuous at a point. Talk later about continuous on an interval. Okay, I'm hoping you're getting the point. Let's do, I think I got one more for you. Anybody know what function this is?
Tangent function?
This is tangent. Okay.
So we did this in May.
What is the limit as x approaches pi from the left? 0. What is the limit as x approaches pi from the right?
0.
What is the limit as x approaches pi? 0. So as x approaches pi over 2, this just keeps getting larger and larger and larger and larger and larger. So we put positive infinity. The limit as x approaches pi over 2 from the right? Negative infinity. Approach to the right. This just keeps going down, down, down forever. And what is the limit as x approaches pi over 2? Does not exist. Because this doesn't equal this. If they both go up to positive infinity, we say we put positive in here. They both go down. But if they go in different directions, definitely doesn't exist. So is it continuous at pi over 2? Definitely not. In fact, what is tan of pi over 2? Does not exist. Okay. What do we call this type of discontinuity? Asymptote. We used to call it infinite discontinuity. So a hole in the graph, we call a removable discontinuity. If it jumps, it's called a jump discontinuity. Okay. This is this function of sine of pi over x. Okay. It's continuous everywhere except at what?
0.
X equals 0. You plug in any number here but 0, we know sine of that value. Okay. The interesting part, the limit as x approaches 0. Okay. To get closer to 0, what's happening? So let's look at this. As x goes to 0, what's happening to this? What's pi over a very, very small number? like pi divided by 0.00001 is very big number.
Big, very big.
And the closer you get to 0, the bigger the number gets. And what is sine of a very, very big number? It just keeps doing this forever. It keeps oscillating. So the closer we plug in values to 0, the closer the inside goes to infinity, and sine just keeps oscillating back and forth. You get this really cool graph. So this, both from the left and from the right, don't approach a single number. It'll never be greater than 1. It'll never be less than -1. But it does not approach a number, so this does not exist. This is called an oscillating discontinuity. It's actually really cool if you look at on Desmos. Okay. The more I zoom in, the more there are. It completely fills up the whole screen. They're really right. There is a little gap between every single one of those lines. But the closer you get, the faster it goes back and forth, back and forth. Super cool. Okay. Very weird as well. But there we go. Okay, I think we're going to stop here. Again, all the limits, the idea of left-hand limit, right-hand limit, the limit is only based on tables of values and graphs. And then Friday we'll talk about when we're just given the actual equation of the function. I put a new delta math assignment up, so just do delta math. So you can get going on that.